Okay, we're going to do a numerical problem this time, having to do with Faraday's law. It's going to be a two-part problem. Part A gets you prepared to solve Part B. Now, just to set you up, we've got a square here, and the single turn wire loop is referring to this square right here. The circle that is surrounding it is not a single hoop. That is actually a solenoid that you were staring down the barrel of in this problem. Okay, so give it a shot and see how you come out and if it's the same as what I got. Alright, I'm going to get started. Let's start with part A, okay? This says a square, the square loop inside has a certain length. It's a square centimeter here. And we got a circular cross section of 3 centimeters, right? Now, that 3 centimeters here is actually not going to matter. It doesn't play into our equations anywhere, as we will find out. The solenoid is 20 centimeters long, so if we were to view this from a different point of view, then we would see a 20 centimeter long tube with a solenoid wrapped around it, essentially, right? And 100 turns of wire, so the number of turns, capital N, is equal to 100, and that is evenly distributed over the 20 centimeters, we presume. Okay, so we, in part A, are told that the current is going to be 3 amps. So we can now find, then, the magnetic field inside our hoops, our solenoid, right? Alright, the magnetic field inside the solenoid is, of course, given by our solenoid equation, mu naught lowercase ni, where lowercase n is the coil density and is equal to the number of turns per unit length, okay? So, unfold everything here. That's mu naught. We have 100 turns every, this is 20 centimeters, so every 0.2 meters. And we are pumping 3 amps of current through this. So, that provides a magnetic field of 6.28 times 10 to the negative 4 Tesla, or about 6.3 gauss. So if that is our magnetic field, what we're actually asked about in part A is not the field, we are asked about the flux. So what does that make the flux? Now we know that this square is face on with the field here. We don't actually know that, but it implies that with the drawing. So then the flux is going to be such that we have magnetic field times area of our square, because we're not considering the magnetic field outside the square. Only the magnetic field inside the square contributes to the flux in the square. So area of the square, and then times the cosine of the angle between the B field and the normal to our square. But those are in the same direction, so that will go to 1. Okay, that's going to be 6.28 times 10 to the negative 4 Tesla times the area, which is 0.01 meters by 0.01 meters, 1 centimeter by 1 centimeter. And that brings us down to 6.28 times 10 to the negative 8 Tesla meter squared, or Webers. That is going to be our answer to part A. For part B, now that we know the flux, we can continue. If the current in the solenoid is reduced to 0 in 3 seconds, that means our time value is going to be 3 seconds. And our flux initial is 6.28 times 10 to the negative 8 Webers, then our flux final is actually going to be 0, right? Okay. What is the magnitude of the average induced EMF in the square loop? When we say average, all that means is we didn't necessarily ramp it down in a like one-for-one way, but you know, we know that where we started, we know where we ended, so we just take the average EMF. Anyway, so that gives us this equation. Remember, the negative sign is just there for math reasons. N is the number of turns in the hoop that is experiencing the flux change. That would be this hoop, right? If you've got a battery attached, then that's not the one you're looking for. N represents the one that is experiencing the flux change. This says the square is a single turn wire loop, so that means that N is equal to 1. The change in flux is going to be our final flux minus our initial flux, which is 0, minus 6.28 e to the negative 8, and all that divided by 3 seconds. It's quite a small amount of voltage. 2.09 times 10 to the negative 8 volts. Okay. There's our answers. I'm going to go ahead and clean this up. Okay, and there's my answers. Hopefully yours are the same. If not, go back and see where you and I did things differently.